All right. I'm back. I was just talking with someone, and they were asking me about a different way to perform the 2 point the the convolution of h1 of t from 2.22d. So here's h1 of t, and I thought it was kind of interesting, so let's go over it. So here's h1 of t, and this is the same as we had it defined up here before, up around this area here. All right, and so instead of doing it like we did in the last one, what we're going to do is we're going to see if we can get the same answer again, doing it a different way. So what we're going to do is we're going to break h1 of t into two different things, and then we're going to convolve each one of those with x of t. So here is, so h1 of t, let's say it's equal to h1 1 of t plus h1 2 of t. So here's h1 1 of t, or when we put in the tau axis, we can call it u of tau, and then here's h1 2 of t, call it u of tau minus 1. And now we're gonna flip our x. So we have x of t minus tau, and we're evaluating it at t equals 0. And now instead of passing the unit step, the pulse of with 1 through x, we're going to pass x through each one of these unit steps, and we'll do the analysis, and we'll see what we end up with. So y1 of t is going to be equal to, that's going to be x of t convolved with h1 of t, which that is, so we can apply the commutative property here, so we'll get h1 of t convolved with x of t, and then we'll change out h1 of t, so we have 4 over 3 times u of t minus u of t minus 1, and that's going to be convolved with x of t. And keep going here, and we're going to now apply the distributive property, so we get 4 over 3 u of t convolved with x of t minus 4 over 3 u of t minus 1 convolved with x of t. And we can roll right in and immediately set up our integrals because we know what they're going to look like. So we get y1 of t is going to equal the integral over all time of 4 over 3 u of t, or excuse me, u of tau. Let me rewrite this. I'm going to put that 4 over 3 up front. 4 over 3 u of tau times x of t minus tau, d tau. And then we have a minus, and it's 4 over 3, the integral over all of time, u of tau minus 1, x of t minus tau, d tau. All right, and now looking at this, looking at each one of these, we really don't even need to worry about how we're going to, the bounds of our integrals, because we have some unit steps here, so it's pretty easy. We know that in this top one here for the unit step evaluated at tau, that everything this in this area is going to be equal to 0. And with u of t minus 1, we know that everything over here is going to be equal to 0. So both of our integrals, the upper bound is going to stay the same, but we have to change the lower bound. So for u of tau, we're changing it to a 0. So we have from 0, and let me just put that 4, 3 all the way up front, going to infinity, and x of t minus tau, d tau, and then minus from 1 to infinity, x of t minus tau, d tau. And now we can change out we can change out x of tau, or we can change x of t minus tau. So that's going to be 4 over 3, the integral from 0 to infinity. Oh, I got to put that big bracket on there, don't I? 4 over 3, the integral from 0 to infinity. So we have a times, and now we have to change out. We have to swap out. Like right here, we have x of t, right? And here's where this t comes from. Well, we have t minus tau, so now we need to swap out t for t minus tau. So t minus tau plus b, and this whole thing is being multiplied by d tau. Put another parenthesis there. Minus the integral from 1 to infinity, a times t minus tau plus b d tau. And I'll do it all the way over here. All right. And when we do that, let's do, it's going to be 4 over 3 now, because we have an improper integral here. We're going to say the limit as alpha approaches infinity of the integral, and this is going to be on both of these, the integral from 0 to alpha of a times t minus a times tau plus b d tau, and then minus the integral from 1 to alpha of a times t minus a times tau plus b d tau. So we have the 4/3 out front. We changed we replaced our integral that was our improper integral. So now we have it in the proper form because we're taking the limit. We multiplied a times t and then a times negative tau and then the plus b. All right, so we're looking good so far. And then we're just going to work through it. We have 4 over 3, and that's going to be times the limit as alpha goes to infinity of, and now we do our integration. So we will have two things here. Got a lot of brackets going on. We'll have a t tau minus 1/2 a tau squared plus b tau, and that's evaluated at infinity, or excuse me, at alpha and 0, minus, and we have the same thing just with the different limits, or different endpoints, a t tau minus 1/2 a tau squared plus b tau, and we're evaluating that at alpha and 1. And we have a parenthesis, and then we have a bracket. And we're almost there, so we have y of t, and now we're just going to evaluate, do the algebra. So we have 4 over 3, and the limit as alpha approaches infinity of, so the first one here, it'll be a t alpha minus 1/2 a alpha squared plus b alpha, and then we have a 0 going to each term, so it's all going to be zeros. So now we can move right on to the next one. So we'll have a minus sign, excuse me, and then we'll put it in some parentheses so that we don't get our signs confused. We will have a t alpha, we're over here now, we're doing this one, evaluating at the top point, minus 1/2 a alpha squared plus b alpha, and then minus. And now we're evaluating at this point. I'm not going to add any more parentheses. I'm just going to use a sign. So we have to evaluate. Oh man, big boo boo. So we have a t tau, and we need to evaluate tau equals 1. So that's going to be at, and then a minus times a minus 1/2 a tau squared, with tau equal to 1. So that will be minus, now that'll be plus 1 over 2a, and then a minus positive b tau, with tau evaluated at 1. So that'll be a minus b. And we'll write it out again, because I'm trying not to get confused on any of the signs, because I make the most mistakes in like math with basic algebra. So we have y1 of t, and that's equal to 4 over 3, and that's the limit as alpha approaches infinity of a t alpha minus 1 over 2 a alpha squared plus b alpha minus a t alpha, and minus plus 1/2 a alpha squared minus plus, so minus beta alpha minus and a minus plus a t minus and a plus minus 1/2 a, and then a minus and a b. So that's a plus b. And if we go through and cancel some stuff out, well, we see that that goes away, and that goes away, that goes away, that goes away, this goes away, that goes away. And what we're left with is that's equal to 4 over 3 alpha times t. Now let's distribute that 4 over 3 in here. And then minus, so we have 4 over 3 times 1/2, so that is 2 over 3 minus 2 over 3 alpha plus 4 over 3 b. And that's y1. So that's just that we left the impulse off. Now the impulse, when we did the convolution of y2, that was our impulse, and we have that right there. So I'll bring that back down. So we have y of t is going to equal y1 of t, which is 4 over 3 alpha times t minus 2 over 3, or not alpha times t, a times t minus 2 over 3a plus 4 over 3b, and that's minus y2. And let's get this y2 out of the way. Put that y2 up there. So minus y2, we're going to distribute in this 1/3. So we have minus 1 over 3 at, and then a minus and a minus. So we get plus 2 over 3a, and then a minus and a plus. So minus 1 over 3b. And when you do the math, so we have a 4/3 at minus 1/3 at. So we have at, a minus 2 over 3 alpha, or a plus a 2 over 3a. So those cancel. And then a 4/3 b minus 1/3 b. So that gives us plus b, which is equal to x of t. And that's the same answer that we had before. So there's another way that you could do it. Might be, I think there's maybe a little more writing to do, but it might make it a little bit easier trying to set up your bounds, see what you're integrating over. Let me, I'll erase some of this and put it all kind of on the same thing. So that's all going to shift up here. Let me just hit the, but Yeah, so that's another way to do it, and you're gonna arrive at the same result. So, all right, thanks.